The first part of 7.2 is looking at position of equilibrium, and with that we're looking at the equilibrium expression. Okay, so we have a constant, the equilibrium constant, and that is our Kc value. Just like in the rate expression where we have the value K is the rate constant, here Kc is the equilibrium constant. It is a fixed value for each reaction at a specified temp. Therefore, it is temperature dependent. Every reaction has its own particular value for Kc, therefore it has to be calculated with every different reaction. How do we go about writing the equilibrium expression? If we have a generic reaction, so little a bit plus next to big A, we have the little ones are our coefficients, and the big ones are our compounds. Unlike the rate expression, we can create, or unlike the rate expression where we cannot determine the rate expression from the stoichiometric equation, we can do that with our equilibrium expression. Everything we need is in the stoichiometric equation. And what we have to keep in mind is everything in a reaction is based off ratios. Therefore, if we're looking at concentrations in equilibrium, we are looking at the ratios. How we go about finding or determining the equilibrium expression. We have Kc set to C to the exponent of the coefficient for C and D to the coefficient of D. These are our products. We divide those by our reactants. It's the same situation every time on how to set this up, as long as you have a completely written and balanced reaction. Here is an example of how we write a chemical expression. We have the reaction H2 plus I2 gives us 2HI. It is an equilibrium expression due to the double arrow. To write the expression, we take the concentration of HI and take it to the power of 2 because products go on top. I write the EQM next to this just to tell you that the concentration that we put in these brackets are the concentration at equilibrium, and this will come in later. Not the initial concentration, but when we're at equilibrium, because we are working with the equilibrium constant. Below, we have the reactants, and both of those concentrations at equilibrium. Because there's no coefficient in front of them, we do not need any exponents at this time. I've provided two examples of how to use this calculation. So in example number 1, we had a different set of initial concentrations, and we let the reaction go to equilibrium. And these are the concentrations at equilibrium. So we have 0.156 molar, or concentration of HI, and we take it to the squared value. We divide it by the two reactants concentrations at equilibrium. When you do the math, you get 49.4. We did the same thing, but starting with different initial concentrations, which gives us different equilibrium concentrations, but when you do the math, you still come out with 49.4 for your Kc value. That means that your equilibrium is at the same position. It did not change, which means those concentrations are within the same ratio in which we had originally. It's not until you stress the system by changing the temperature, by changing the pressure, anything along those lines, will you change the Kc value. As you notice, Kc has no unit because it is just representing an activity that is going on within this system. So what does the Kc value actually mean? If that value in which you calculate is above 1, like we saw, 49.4, that means our products are favored. The products are being favored because the larger number or the larger concentration is on top of that reaction. Therefore, the equilibrium lies towards the product side, therefore the reaction tends to go towards completion. And so if we look at the previous reaction with the 49.4, that is above 1, therefore we are favoring products and tend to go towards the completion side of production. If that Kc value is less than 1, and I'm not saying a negative number, I'm saying a decimal value like 10 to the negative 3, so on and so forth, that means the reactants are favored because the larger number for the concentration value is on the bottom of that mathematical equation. And this means the reaction barely starts and we have very little product to reactant.